All right, mathletes, let's do this. We're looking at homework 22, section 3.3. So I wanted to go over a few problems together with you. So let's just jump into this. Number one, they want you to write this equation in exponential form. So if you watch my other video, we talked about that. So when you're looking at logarithmic form, you always identify the base. The base is 7 here. So there's our base. And we always raise our base to the exponent, so that 2 is our exponent, and it's always going to equal the argument, which is 49. All right, so this is what we call exponential form. And then some problems are they look a little bit more complicated. For example, number 2, just because there's a fraction, and if you notice, they don't actually write a base. So when there's no base written, you just say there's invisible 10 there. All right, so here we have 10 raised to the power of -5, and what that equals is it equals the argument, which is 1 over 100,000. All right, so this is exponential form. And now for number 3, notice what they want. They give you exponential form, but now they want logarithmic form. So logarithmic form, again, we write log. We want to identify the base. The base is 7. The base is 7. And then it's always equal to the exponent. So the exponent here is 2. So that's what's going on the other side. And the argument, all right, this piece right here is right here. So what this is really saying is when you have log form, translation is 7 raised to what power gives me 49. That's what that translates to. All right, so these will take you through the first 3 problems. All right, let's look at the next portion. All right, let's look at question 7 here. So again, you want to simplify these without using a calculator. Notice they give us this ln. What the heck is a ln? Well, ln is really the same thing as writing a log with this particular base. The base, the number that we're looking at here, is e. And again, if you looked at previous homeworks, you learned that e is a special number. E is approximately 2.718. All right, so very special number. So ln, right? Whenever you see ln, think about it as log base e. So now when I rewrite this, right, I'm going to rewrite this right now. This is really log base e of e to the 9th power. All right. So we're going to learn some properties, but I want to explain to you why some magic's about to happen. All right, so let's look at this. Let's say this is equal to x, just to kind of walk you through the thinking here. I'm asking you the base raised to the exponent, so e raised to the power of x equals the argument, e to the 9th. So since these guys have the same base, that means their exponents have to be the same. So x has to be equal to 9. So let's kind of take a step backwards here. Notice these two, you could think about these two as canceling each other out, right? And we're just left with that 9. Well, that's actually one of our properties. So one of our properties, I'll put one of our log properties, and I'm going to go over all these in a summary with you, says that if you have, say, log base b of b, and let's say we raise it to the x power. Whenever the base and the argument are the same, think about it as this whole thing canceling each other out, and you're left with x. All right, and that's exactly what happened up here. So this answer just turned out to be 9. All right, let's look at number 8, because in question number 8, we could use the same fact, right? So these two have the same base, and the argument are the same, so they cancel out, and we're left with that exponent. So we're left with 13 for that answer. For question number 9, these two are the same, And notice there's no exponent, so if you want, you could actually write an exponent. You could write a 1 there. So our answer, boom, is 1. Again, for number 10, we just learned that ln and e, they really cancel each other out. And it's hard to see here, but this is the actual exponent. So ln and e, they're the inverse function of each other. They cancel each other out. So you're left with u squared plus 3. All right. And let's look at question 11. So for question 11, what we're going to do here is I'm going to do something creative. I'm going to rewrite 1 over 49. All right. Here's the reason why. Let me walk you through this. This is the base raised to something equals 1 over 49. Whenever you have a fraction here, all that means is we're going to have a negative exponent. All right. And you ask yourself, can you rewrite this 1 over 49 as 7 raised to some power? Sure. So 7x, nothing happens there. 1 over 49, that's just 7 raised to the negative because it's a fraction. And 7 raised to the second power gives you 49. So this is the same thing as this. All right, because 7 squared gives you 49. And since this was a fraction, all that means is my exponent's negative. And once again, they have the same base. So that means the exponents have to be the same. So this is one way of answering that question. The other way, using our property that we just talked about, that one right there, I could rewrite this log. So instead of writing 1 over 49, oops, I forgot my base. I could rewrite that as 7. 1 over 49 is really 7 raised to the negative second power. And the reason I want to write it that way is because now I see my base and my argument are the same. And so we know that we're just left with that exponent, which is negative 2. Same thing that we got over here. All right, so we're going to be very creative in this section here. All right, for question 12 here, notice they want us to graph these logs. So I'm going to use my friend decimals here. And some things I want to point out. Any type of log function, it's always going to have this x-intercept. So let me actually point at it so you guys could see. This point is 1, 0. That's always going to be my x-intercept of these basic log functions. But now notice what happens when I put that minus 6. So notice, because this is happening to the x value, we've talked about this in the past. All right, so let's go ahead and let's get another log function. Let's throw another log function in the mix. And same base 3. But now let's do x minus 6. And what you could see is, just as we noted before, this minus 6 is really going to move. It's going to shift the graph 6 units to the right. And that's what you're seeing here in our graph. So let me move this so you guys could see. And what's going to happen is we're always going to have this asymptote, this line here, that we're never going to cross. In this case, this invisible line, this asymptote is going to be at 6. And in the next problem, I'm going to show you how to find the asymptote of these logs. So this blue line represents this function right here. And all you're going to do for question 12 is match it up. So we're slowly starting to see, how do these logarithms look? Alrighty. All right, so now they want to talk about the domain. So for the domain, one thing about logs is that our argument is always positive. It's always positive. So what we do is you take that x minus 6 and you make sure that's always greater than 0. And now we solve like we normally would. So we add 6, and you have x, in this case, always has to be greater than 6. So that's why when we actually saw the graph, the domain were all the values of x that are greater than 6. So this represents our domain. So it's from 6, we don't include it, all the way to infinity. And then for the range is always all real numbers for these logs. All right. And so because we don't include, right, in our domain, this 6, that's our vertical asymptote. So for this question right here, our asymptote here, we have x equals 6. All right, so again, the key is when you're looking for the domain of these logs, we take that argument, whatever it is, and we make sure that it's strictly greater than 0. And moving to question 17, question 16 is pretty similar. And the other questions I skipped over are more graphing. So again, they're just looking for the domain here for question 17. So what did we just say? You take the argument and you make sure that's strictly greater than 0. All right, so in this case, I think we're pretty lucky because we could factor this. We get x plus 7, x plus 1. If you need help with factoring, go ahead and check out my YouTube videos. They're under the algebra playlist, and I have a whole bunch of examples of how to factor, all right, for you. And this is greater than 0. Remember what we do? We find our boundary points. So we set these two, each one of these equal to 0. And we're going to get x equals negative 7 once you set that equal to 0. And then we're going to get x equals negative 1 after you set this equal to 0. Those are our boundary points, if you recall. So I got negative 7. Right? And what we're going to do is we're going to test the point to the left and to the right of negative 7. Let me write that a little darker. Negative 7. And then we got negative 1 somewhere. And then we're going to test the point to the left and to the right of negative 1. And remember what we're looking for at the end of the day. Whatever numbers you plug in, this better be greater, this whole side better be greater than 0. That's what we're looking for. So let's go ahead and let's plug in our test point, negative 8. So what I'm going to do is I plug in negative 8 right here, and I'm going to plug in negative 8 right here. So when I plug in negative 8, I'm going to get a negative in that first, right? Because I plug in negative 8 right here, that gives me a negative, because I'm going to end up with negative 1, times, so I put my times, and when I plug in negative 8 right here, I also will get another negative. I don't care what that number is. I'm just interested in the sign. So my final result is a positive, and that's exactly what we're looking for. So this whole region over here is going to be part of our solution. All right, let's pick a number now that's between negative 7 and negative 1. So I'll keep it small, and I'll say, let's plug in negative 2. So we're going to have two parentheses, and again, I'm just interested in the sign. So when I plug in negative 2 right here, I get negative 2 plus 7. Well, that just gives me a positive 5. So that's a positive. And when I plug in negative 2 right here, that gives me a negative. And we know a positive times a negative gives us a negative. So this is not going to be part of our solution. All right, last, let's pick a number that's greater than negative 1. So I'll plug in 0. Easiest number in the world to work with. So I plug in 0 here, and we see we get a positive. And when I plug in 0 here for this x value, we get a positive. And so when we multiply those, we end up with a positive, and that's exactly what we're looking for. All right, so our interval, right, are all the numbers from negative infinity, that's not it, negative infinity, all the way to negative 7. We're not including those because you don't want it, you want it to be strictly greater than 0. And then from negative 1 all the way to infinity, and then make sure you put the union to glue those two together. All right, folks. So there's our domain. Hopefully this video is helpful for section 3.3. Don't forget to like, subscribe, and I'll see you all in the next video.